Okay, we've got a further maths differential equation problem here. Let's just go full screen, which is quite a tricky problem. This is actually from the Excel specimen paper, um, but this is actually kind of quite a good model for the sort of problem that you can get in further maths. Okay, so we've got it's got a few different. We've got a density in here, which is kind of a bit difficult to work with. We've got we've got use of an integrating factor here, and so on. So yeah, it's a little bit of a challenge. Let's have a look at the problem. Pond initially contains 1,000 liters of unpolluted water. Pond is leaking at a constant rate of 20 liters per day. Here we go. Here's the pond. All right, there's 20 liters per day uh, leaking out of it. Um, Contaminated water flows into the pond at a constant rate of 25 liters. Yeah, there. And the contaminated water contains 2 grams of pollutant in every liter of water. So I've kind of divided this up here. So we've got our volume sort of perspective here on the left, and on the right, we're sort of looking at the amounts of pollutant. So if there's 25 liters per day going in, with 2 grams for every litre of water, then there's 50 grams of pollutant going in. Here's our 20 litres coming out. Um, right, so the tricky thing here really is that we've actually got grams of pollutant actually leaking out, but that's not quite so easy to, not so obvious to see. Um, Now there are A levels questions here where we've got 3 variable problems. I mean, this is kind of three variables, maybe more arguably. There's one which is kind of similar kind of thing, water um, entering and leaking out of a cylinder. Um, and we can derive the sort of target derivative fairly straightforwardly on this. But whereas this may be true here as a general statement, dx dt equals dx dv times dv dt. Yeah, we do know what dv dt is. We can see that from what's happening here. But dx dv is rather more difficult because the density of the pollutant is actually changing over time, isn't it? So we've got we start off with unpolluted water and then we've got polluted water leaking into it. Okay, so and then it mixes. So what comes out, so initially you can imagine in the first unit of time, there's 20 liters, there's 2 grams of pollutant gone in, but the same hasn't come out. So, so the density is changing, and that's what makes this tricky. But as I say, this is a kind of form of problem that will crop up. So let's just have a look at the density. So the density is basically this, isn't it? It's x divided by v. These are functions of time. X is a function of time, V is a function of time. So if that is the density, then the rate that the pollutant leaks out is going to be this 20 times the density. And if you just kind of want to just convince yourself that the density is in grams per liter, all right, and the rate of leaking out is in liters per day, L divided by D. So when we look at we analyze the units, so the L's, the liters cancel out, we just end up with grams per day. So, which is what we want, the rate of pollutant leaking out. Okay, so that's kind of good check just to check that the units cancel. correctly. Okay, all right. So now we've got a sort of a reasonable statement here of what is happening with the pollutant. So the rate of change of this is the net. It's what's going in minus what's going out. So we could simply write that dx dt equals 50 minus this thing here, 20x over v. Right, what else do we know? Well, we know that I mean, we've got V here. We can actually substitute that because we've got this sort of analysis here. So the actual volume in the tank, well, it starts off as 1,000. We are adding in 25 every unit of time. So the volume is going to be 25 times T, but then being decreased by what's leaking out, which is 20 units of water per unit of time, so 20T. So that's going to give us V equals 1,000 plus 5T. Right, okay, well, there we go. We're sort of almost there now. So if we just do that substitution for V, we're going to get this statement here, a bit of cancellation, and we're going to give that, get that, which, lo and behold, is what we have been asked to derive. So that I think I personally think that's a little bit awkward. We just have to kind of spot the role of the density in there, and this sort of problem that we're going to encounter in further maths. Yeah, he's full of these sort of, he's got these compound measures that we have to take account of. So densities, compound measure, grams per liter. So that's a sort of a theme with these kind of problems. Now, so we've got our differential equation, arguably the hard part. In actual fact, the we found that. So we now got to find the number of grams of pollutant in the pond after 8 days. So we want our relationship between x and t. So in other words, going to have to solve our differential equation to get to a relationship between x and t. So this is the sort of the form of thing that we want. This is our kind of standard reference thing. So if we have an equation of the form of this, then we derive this integrating factor, multiply through all the terms by the integration factor, and the integration problem becomes relatively straightforward. Okay, that's so there's other texts and resources actually dealing with that method, but that's just a reminder of what we're doing. Anyway, here it's not y and x, it's x and t. So so that is our that is our equation there. So just rearranged. Yeah. So we've got the constant. Well, it's constant, but we got regarding that as being a function of t essentially. So it's the right hand side. Okay, so that's a rearranged form. So our p of x is this. And therefore our integrating factor is e to the power of the integral of the integrating factor with respect to time. Ooh. Right. Okay, so that integral itself is sort of fairly straightforward. 1 over 200 plus t integrates the natural log of 200 plus t. We've got 4 times that. But of course, that is the same as e to the power of the natural log of 200 plus t to the power of 4. And then e and natural log of functions and inverse functions. So that then simplifies to that. Right. Okay, so you might need to just kind of pause and just have a think about that. But that's essentially what we've got for our integrating factor. So the process now is that we multiply all the terms in there by our integrating factor. Okay, and that's what we have done there. So we multiply this by that, we're going to get 200 plus t cubed. Yeah, there's our 4 from here, and there's our x from there. And then the right-hand side is just 50 times this. Right, now the point with this is that when we are in this particular form here, then you should be able to spot that actually what we've done is we've differentiated using the product rule. We've differentiated that with respect to t. Okay, so in other words, let's just work backwards on this one. So we're going to the derivative of that times that plus that times the derivative of that is what we've got. Okay, so that's yeah. So we've got the derivative of x times the second term in the product plus the derivative of this, which is going to be 4 times 200 plus t to the power of 3. Okay, that's just the power rule, isn't it? And that's equal to yeah, well, that's differentiation product rule and equals the right-hand side. Right, now if we integrate both sides of this, and this again is the method we use for this type of differential equation, then we're integrating the derivative, so we're just going to end up with that term. And then we're integrating 50 times this thing here. Well, that's going to simplify to this essentially. Again, that's just the power rule, isn't it? Yeah. We can do a substitution if we like. U equals 200 plus t, but really there's kind of not much advantage in doing that. So that's what we got, plus our constant of integration, of course. Now we are also given indirectly this boundary condition is that at time t equals 0, there is no pollutant in the pond. So if we actually substitute those into our general solution here, then basically that's going to give us that c is equal to minus 32 times 10 to the power of 12. And then we can actually substitute that in there in order to give us this particular solution for x. Right, so that is it. A bit of an ugly looking thing, isn't it? But that's what we've got. Right, so that is part B. Now, if we continue on part B, then we're simply asked to find the number of grams of pollutant in the pond after 8 days. So this is just a substitution of t equals 8 in our particular solution here. And this is basically just gonna, you can see how it works here. Pause it again if you are not sure, but we're just substituting 8 in there, working it through, and we're going to get this figure. 7 decimal places. I mean, the question doesn't actually specify how accurate it wants, but yeah, you can do whatever accuracy you like. Okay, so that's that, and then there is a last part here, which is explain how the model could be refined. The general thing with all these is that we've got to look at the assumptions in the question, because the assumptions are usually simplifying assumptions, and if they're simplifying assumptions, they're going to make the model well, easier to work with. Obviously, they're easier to do our calculations and easier equations and so on. But of course, it introduces inaccuracy. So if we wanted something which was going to be more accurate, and that's what this is implying, then we need to kind of take account of, we need to remove the assumptions and take account of, in this case, the rate of mixing. How we would do that, I don't know, but we're not actually asked to elaborate any more on that. So yeah, just made a note there. Look at the assumptions. That's usually the key to how you answer these bits. Right. Okay. So Okay, well, hopefully that has been useful. So kind of quite a nice problem and fairly typical, if you like, of this sort of problem. So thanks for watching.